we are meeting again in the lecture series under the caption Statistics and Management Studies. Earlier, I discussed 3 sessions in queuing theory. Queuing theory is very important in management studies. In nowadays also, the online purchasing, online marketing is more significant. So, queuing theory has more and more significant in management studies. That is, physical queue, virtual queue, etc. are advancing. So, in management studies, I am discussing today about the significance of lambda and mu in MM1 model again, and some problems and introduction of MM2 model. As we know, lambda is the arrival rate, mu is the service rate. Lambda has no control. The arrival rate has no control by the entrepreneur. The entrepreneur can control only the service rate. So that is the most important thing also. And one more thing about the statistical application, arrival rate and service rate is related to cost, money cost. Service time cost, arrival is the queuing cost. Both the costs are to be minimized. What are the two costs? One is the waiting time cost, other is the service cost. Both are having negative correlation, both are to be minimized. That is the challenge before an entrepreneur. One more problem in MM1 model is discussing here. Whatever be the terminology of the problem, that is a shop or a bank counter or an automobile shop or a post office or a telephone booth, whatever it may be, we need 3 factors. One is only one server, that is a single server model. Other is lambda. Lambda is the number of arrivals in a fixed rate. So I am discussing this problem. Here lambda is not given. It is given that a customer is arriving in 12 minutes. One customer in 12 minutes. That is, inter-arrival time is 12 minutes. Therefore, what is lambda? Therefore, lambda is the number of arrivals in 1 minute or number of arrivals in 1 hour. For convenience, I am taking the number of arrivals in 1 hour. In one customer in 12 minutes. So in 1 minute, 1 by 12 customer. In 1 hour, 60 by 12. That is 5 customers in 1 hour, 5 per hour. That's the arrival rate. What is mu? It is given that the service time for a customer is 10 minutes. 10 minutes. There is the other information, 10 minutes. That is, in 10 minutes, 1 service. Therefore, in 1 minute, 1 by 10 service. Therefore, in 60 minutes, that is 60 by 10. That is 6. 6 per hour. That is, the arrival rate is 5 per hour and service rate is 6 per hour. Then we can compute the odd terminology related to this using lambda and mu. This is the important thing, that both the units are having the same time interval. Lambda is equal to 5 per hour and mu is 6 per hour. That is, lambda is equal to 5 per hour and mu is equal to 6 per hour. That is the requirement for a MM1 model. Lambda is less than mu. Using this terminology, we can calculate all the factors related to a MM1 model. Then what are the questions, possible questions? What is the traffic intensity? What is the utilization factor? What is the probability that system is active? Or from the point of the manager, the question is how much time that system is active. That is lambda by mu. Lambda by mu. Traffic intensity, probability the system is active, utilization factor. we discussed in the previous problem. So lambda by mu is the percentage of time that system is active. That is the most important from the point of view of the manager. He wants that, or his requirement is the system should be active. That is 5 by 6. Then a customer is interested when the system is not active. He will get service immediately after joining the queue. So his interest lies in the idle time. The probability that system is idle, or what is the chance that the queue is empty? It is 1 minus lambda by mu. That is 1 minus 5 by 6. That is equal to 1 by 6. Then we can calculate the different components. What is the number of units waiting in the system, number of units waiting in the queue, the time spent in the system, etc., etc., discussed in the earlier problem. Please refer that one. One more thing. What is the probability that the system is active? When will the system is active? Probability that at least one person in the queue, one person is waiting in the queue. That is traffic intensity, lambda by mu. That is the system is active. So we are calculating or suggesting other factors also. One is about the number of units. Number of units, number of items, number of physical units waiting in the queue and waiting in the system. First I introduce waiting in the system. That is a formula, lambda by mu minus lambda, 5 by 6 minus 5, that is 5. 5 units are waiting in 1 hour, 5 per hour. That's a unit, 5 per hour. How many in the queue? Lambda square by mu into minus lambda, that is 25 by 6 per hour. And about the time, how much time, that is important for the customer. How much time a customer spent in the system? 1 by mu minus lambda, 1 by 6 minus 5 equal to 1. What is the unit of 1? We discussed lambda and mu arrival rate, service rate in 1 hour. Therefore it is 1 hour. That is, a customer has to spend 60 minutes in a system. That is a single server queue. 10 minutes for a service. When he entered into a service, he required only 10 minutes for service. So how much is to be spent? By formula, that is lambda by mu into mu minus lambda, 5 by 6 hour. 5 by 6 hour, that is into 60 equal to 15 minutes. 15 minutes. That is a simple logical point. 60 minutes, 15 minutes in the queue and 15 minutes for service. 50 plus 10, that is 1 hour, that is 60 minutes. 60 minutes. And what is the probability that system remains empty when a customer is arriving? 1 minus lambda by mu. And how when system is active? Lambda by mu. That is defined in terms of probability. What is the probability that n units in the system? 1 minus lambda by mu into lambda by mu. At least n units is lambda by mu. Therefore, what is the probability that system is active when a customer is arriving at the queue? That is lambda by mu. That is 5 by 6. That is the traffic intensity, utilization factor. All these factors are discussed in the earlier problem also. So this is one more problem in M model under knowledge category. Now I am introducing one more problem in understanding category. One more problem in M1 model is discussing here. This problem is different from the problems that we discussed earlier. This is a problem of under category application. It's a problem of decision making by an entrepreneur. In earlier problems we computed the components of a queue, but the problem is different. Let us see the problem. The breakdown rate of machines in a workshop is 6 per hour, and the productive time cost is rupees 20 per hour. The entrepreneur has to go for a technician. The data is two technicians are available, technician A and technician B. The first technician's service rate is 8 per hour. He repaired machines, 8 machines in 1 hour, and he charges rupees 10 per hour. Whereas the technician B, the service rate is rupees 12 per hour, and his service cost, is rupees 14 per hour. And the firm is working for an 8-hour shift per day. The entrepreneur is inquiring about which technician is to be selected, which one is to be appointed. In the management studies, our objective is to always minimize the cost. That is, the manager is interested in appointing a technician whose cost is, his service cost is less. Let us evaluate the problem. The first case is 6 per hour, that is lambda. The breakdown rate is 6 per hour. Then the productive time cost is 6 into 20, and they are going for an 8-hour session. So this cost is rupees 960. That is the cost of the entrepreneur production. That is the loss. If he didn't use a technician, his loss is rupees 960. 6 machines are breakdown in 1 hour, 8-hour day, and the cost is 20 per hour. Then suppose we are using technician A. Technician A is appointed. What about his cost? Lambda is same. The arrival rate is 6. And the service rate of technician A is mu is equal to 8. Mu is equal to 8. And how many machines are in front of the technician in 1 hour? That is the number of units waiting in the system, the number of units which are breakdown, and the number of units which he is under his repair. That is the number of units waiting in the system. That formula is lambda by mu minus lambda, that is 6 by 8 minus 6, 6 by 2 equal to 3 in 1 hour, 3 in 1 hour. And the total cost is 3 in 1 hour, 3 into 8, 3 into 8 into 20, that is 480, and plus 480 plus his service cost is 10 per hour, 8-hour day, plus 8 into 10 plus 8 into 10, that is rupees 560. Is it okay? That is the number of units not working in 1 hour is 3 per hour, number of units waiting in the system, and the cost is 8-hour day, 3 into 8, 24 machines into 20, that is the product time cost, plus his service cost rupees 10 per hour, 8 into 10, that is 560. If we appoint technician A, the expenditure to the producer is rupees 560. Then let us look for B. The service rate is 12. Mu is equal to 12. Lambda no change. The breakdown rate is 6. Then the number of systems waiting in the queue, waiting in the system, number of units waiting in the system before the technician B, number of units he is repairing plus the number of units waiting for repair, that is lambda by mu minus lambda, that is 6 by 12 minus 6 is equal to 1 in 1 hour. 1 in 1 hour. Then what is the total cost required for B? Total cost, one machine in 1 hour. There are 8-hour day. 1 into 8 into 20. 20 is the per hour cost, productive time cost. Plus, what about his service cost? His service cost is 14. 14 into 8. What is 8? 8 is the number of hours. That is 160 plus 112 equal to 272. Rupees 272. 272. If you appoint A, the cost is 560. If you appoint B, the cost is 272. Which one the entrepreneur prefer? No doubt, no doubt. The repairman will go for the technician B. Technician B, that is the final answer. Since his production cost is, less than technician A. This is a problem of application, decision making in MM1 model. In any queuing problem, the major components are lambda, that is the arrival rate, and mu, that is the service rate. Whether it is in MM1 model or any other model. So in MM1 model, we discuss the condition of lambda is less than mu. We insist that lambda should be less than mu in MM1 model. The number of services that can be offered should be more. The number of arrivals should be less than that. So let us think, what will happen if lambda is equal to mu? Lambda is equal to mu. That is, system is 10% active. Then there is no problem of queuing theory analysis. Then there is no problem of formulating a queue. That's an ideal condition. That's an ideal condition usually which is impossible to occur. Then we are going for a third condition. Lambda is greater than mu. The arrival rate is more than the service rate. That is the third stage, and which is controlled by the entrepreneur. What he will do? He appoint for more servers. The number of server should be more. The simplest example is M2. That is the case of serving the customers by using 2 employees or 2 server or 2 counter. That is the MM2 model. Then if it is more, very more, then we use the MMK model. That is multiple server model. So these three factors determines the type of the queue. MM1 model, single server model. MM2, 2 server model. MMK, multiple server model. Hi dears, we are concluding a series of discussions in queuing theory. Queuing theory is so vast area in management decision. I am trying to introduce the primary idea about a queue in most simple way. Expecting your suggestions, comments to improve the further sessions. Okay, thank you. Please try to inform or try to post the comments below the video you watch. Thank you. The next session we discuss decision theory in management studies. Just like queuing theory, it is also a vast area, decision making. Okay, thank you.